Hello, everybody. Welcome to today's webinar, Cast Cylinder Heads, Why Are They Designed That Way? I am Amanda Harmoning. I'm an admin assistant here at AERA, and joining me from the AERA team is Rob Monroe.
Hey everyone, Rob Monroe here. I look after membership and technical development over at AERA. Another announcement that we've got is our podcasts. So Steve Fox and Chuck Lynch, they do the Engine Professional podcast, and right now episode 11 is gone live. So if you go to our website at aera.org, you'll be able to check that out. If you got a little bit of time this weekend, it's about 50 minutes long or so. And Randy Neal of CWT Industries is who they talked to this week, so on the podcast. And Randy is a wealth of knowledge as far as balancing, and it's just another way to get more information to help you out. And you can get to our website, check the podcast out, and have a listen to that. All right, well, let's bring on Matt Gamble of Banks Power, and Matt is the manager of design, assembly, and testing of the engine programs over at Banks Power, and he has spent the past decade, designing high-performance cast aluminum cylinder heads. And when you think of rocket scientist, man, Matt he really is one, and he's going to tell you about it here in just a little bit. But Matt is a true gearhead, and we are really excited to have him with us today. So, Matt, I'm going to turn the floor over to you. If you got any questions for Matt, by all means, put them in those questions box. And how's it going over there, Matt? What are you up to today?
Oh, good. We're staying busy over here. We got a few things on the dyno at the moment we're testing, and can't talk too much about them because we got some military programs going on, but always a lot of exciting making power, durable power too.
Cool.
But can you guys see my presentation at this point?
We can. Yep. You're up and
All
live.
right.
Yep.
Well then, let's go ahead and get rolling. Again, I'm Matt Gamble, and what I wanted to talk to you guys about today is to provide some insight into the design of cast cylinder heads. As Rob mentioned, I've been doing that for a long time, and I've experienced at trade shows and then talking to customers that most guys just don't have an opportunity to see really what goes into the design side and the manufacturer side of how are the castings made and why are they made that way. So when AERA asked me to do a webinar, I thought this would be a great topic, and hopefully you guys find it enjoyable. I'm going to try to keep it as brief as I can. I mean, I could talk about this stuff for hours, so we'll go through it, and then I'm excited to get your guys' questions at the end. So what we're going to cover today is, first off, talking about why is it that we use castings for cylinder heads. Then we're going to get into the different types of castings, some of the design constraints that I've had to deal with and that cylinder head designers have to work around, and then the casting design itself. So as mentioned, I have a degree in mechanical engineering from Cal Poly in San Luis Obispo. After I graduated, I went and joined Pratt & Whitney Rocketdyne and launched rockets for several years out of Vandenberg Air Force Base, Cape Canaveral Air Force Station. Really, really fun stuff. Got to see some amazing things. But I'm a car nut. I have the disease. I don't want the cure. And so I moved over to Edelbrock and started designing cylinder heads and did that for quite a while. Really enjoyable job. Really learned a ton of stuff. I'm going to share that stuff with you today. And now I'm here at Banks Power. I got an opportunity to work with an industry legend. I got to work with Vic Edelbrock. Now I'm getting to work with Gail Banks. Pretty exciting stuff. And it's in my blood, and I'll be doing this forever. So let's jump into it and talk about castings. Why is it that we use castings for cylinder heads? It really comes down to cylinder heads being parts that have complex internal geometries. So the outside of the casting is pretty straightforward, but inside we've got our intake and exhaust port or ports, and we've got our water jacket, we've got some oil passages, and to make that stuff easily, castings really lend themselves well to that. And the castings are repeatable, right? You can make the same casting over and over and over again in the processes that we're going to talk about today, and they're pretty accurate. cost-wise also, aftermarket high-performance parts, cost to the consumer is always something that we've got to look at. So castings are a relatively low cost to get a really nice part into the consumer's hand. And based on the amount of parts that we think we're going to make, the different casting types that we're going to talk about are better suited for different volumes. And of course, one of the cool things that we can do is tailor the alloy itself and tailor the heat treat so that we get mechanical properties of casting that will meet the performance threshold that we're trying to reach. So we can alloy a little bit differently on a pour, and then we can go to a T6 heat treat, a T7 heat treat. We can extend the solution portion or the aging portion and really dial in the properties of the metal. And of course, we can make heads out of billet. You can see them out there. They're gorgeous pieces. A lot of really talented guys doing that. And 3D printed parts, either with laser sintering or with 3D sand, which I'm going to talk about a little bit later. And those are awesome options, but they're pretty cost prohibitive for the general consumer. So it does also have disadvantages. We are making parts out of sand. So there are some inherent inaccuracies in the parts themselves just due to the medium with which it's created. Also, each cylinder head that we make has its own unique internal geometry and its own complexities that affect the way that the casting is going to solidify as we pour it, and it changes from a liquid. And I'm going to talk about all aluminum today, so it changes from molten aluminum into solid aluminum. It's got its own unique challenges based on its internal geometry. And shrink is another issue that we've got to deal with as the aluminum goes through its phase change process from a liquid into a solid. It actually shrinks, becomes a smaller volume, more dense during that phase change. So the size of the sand mold and the tooling that's used to create that sand mold is actually made a little bit bigger so that the casting can shrink during that solidification. And then there's core shift and core set. And that has to do with how the molds themselves are put together. And there's just inherently, you have to have some tolerances in there, and it kind of stacks up and stuff can move around just a little bit. So you get a little bit of inaccuracy from that just in the process. So in order to better understand castings, I'm going to go over a little bit of terminology here. So the mold package is basically all the sand pieces or the metal pieces, whatever it may be, that make up the geometry that we are going to create. So the top piece is called the cope. The bottom piece is called the drag. So here we see we've got the drag here, and then we've got cores. We've got an intake core, a water jacket, and an exhaust core here that are set into that drag, and then the cope gets closed over the top of that core package in the drag. A core box is the tool itself that is used to create those sand cores. It's depending on the type of sand you're using, the core boxes are made out of different materials, and they have to have what we call a parting line. So right here on this box, you can see where the two halves split apart, and in the core, you've got this parting line. And that parting line is where the two pieces split. And we have to have draft in there. And draft is just it's something we have to deal with castings and traditional pattern making methods. And it's an angular feature that we have to put into the parts so that the sand, the core box can separate, and you can pull the sand out without rubbing it or breaking it. If it was just straight up and down, you'd get too much interference between the parts, and the sand wouldn't release properly from the core box. So draft is something that we always have to fight in the design to make sure that the cores will release from their box. So the sprue, gates, and risers. So we've got to get metal into the mold, and the way we do that is through the sprue. So in this upper picture, we can see the pour going into the sprue here, and then it's going to travel down the sprue and go into these gates along the side of the casting here and enter into the geometry that we finally want to create. It's going to flow through that, it's going to fill the mold package, and then it's going to go into what we call the riser. And this riser is it's like a bit of a reservoir for molten aluminum. We really want the casting to solidify from the deck up. So it's going to fill these gates, it's going to fill into this, the whole thing is going to fill up, and then that solidification ideally starts at the bottom and works its way up at the top. And as I mentioned with shrink, it's going to start to pull back, and those risers create a reservoir of molten aluminum that can draw back into the mold package and finish filling up that casting mold. So as I mentioned, I'm going to talk about the types of castings that I've really worked with the most and that are the most common in creating cylinder heads. So number one we're going to talk about is green sand. And green sand doesn't get its name from the color. It gets its name from the type of binder that's used and the ability to easily recycle it. So green sand in castings is typically, in cylinder head castings, is typically used for the cope and the drag. And then we use dry sand for the core pieces. And that is due to the strength of the sand in the binder. In green sand, it's not as good as dry sand is. So in areas where we want more definition, we use dry sand. And in areas where we're acceptable with a little bit lower definition, or we can put a little bit of extra draft in it, green sand is used in those cases. And green sand is good because its cost is pretty low because of the ability to recycle it, and it works well for producing a good cost-effective casting. Dry sand. So I mentioned dry sand cores. You can make the whole mold out of dry sand, so you can include the cope and the drag in it, and you're going to get better definition. And it's like when dry sand sets, it's like rock hard. So you can get really good like logoing, or if you've got a detail in a port, like a really thin guide boss, or maybe a fin on the floor or something like that, the dry sand is going to work really well to capture the definition in that and reproduce the geometry that the engineer or designer is trying to create. A little bit higher cost, not as easily recyclable, but again, it's really good for making all those internal cores. And you can also, dry sand is pretty easy to make really big castings with too. And then we've got semi-permanent mold. So we call it semi-permanent mold because it's a steel outer steel cope and drag, and then typically some side pieces that slide together. I've got some arrows on here that kind of show how all these different core pieces here in steel slide away from where the casting is going to be created. And then you use a dry sand core in it for the ports and for the water jacket. So what's going to happen here, if we look at this picture, is all those semi-permanent mold pieces are going to close over, the cope's going to close over the top, and we'll get a pour. You'll create a casting, and then those pieces have to slide back. So you have to make sure that there's draft in the right directions and locations so that those steel pieces can release from the casting, and then you break out the sand cores. So it's semi-permanent mold because you're using a combination of sand cores in a steel mold. So let's talk about some of the design constraints that we have to work around. The head bolts, you can add some, like an LSR, you know, a lower row, maybe an upper row, but moving the existing head bolts, you got to honor that. The bores themselves, those are of course related to where the head bolts are, and then the diameter of the bore is dependent on the bore spacing, where the water jacket is in the block. And so that's a constraint that we just have to deal with in most cases. Water jackets, we got to get water from the block into the head, and we want them to communicate. We've got a head gasket in there that's going to have some controlling orifices, but knowing where all that stuff is and getting communication between the block and the head is very important. So you can be a little bit tricky sometimes with that, but usually you've got those water jacket core prints that you've got to deal with and you've got to match up. Same with oil supply and drains. We've got to get oil up into the rocker system and then back down into the sump. And we typically have to honor where those locations are. You can get a little creative with some different angles on the machining operations or some milling some slots, but you also got to be careful about the amount of resistance that you're putting into the oil system so that you get proper oil pressure up to the top and then you drain fast enough back down to into the sump. And then injectors, you know, I've designed a diesel head, and you know, you've got a centrally mounted injector, and now we've got more and more GDI heads out there. Then in both cases, that injector is interfacing with the piston as it comes up in the bore, and the piston's got some geometry relative to the location and angle and spray pattern of those injectors. So typically that's a constraint that you try not to want to move. Push rods. Push rods are always a big one. And we're not as constrained on push rods. I mean, offset lifters can be done sometimes, and rocker locations can be moved around a little bit so that you can get away from the push rod pinch in the port. You know, that's, if there's any guys out there who are porting heads, you know that is always a spot that you're fighting to get enough cross-sectional area through the port and still be able to actuate your rocker arms. So moving those push rods around a little bit can be done, but because of some of the stuff I mentioned, like core set and core shift and shrink, we have to be cognizant of what's going to happen during that casting process and during the machining process so that we get enough material in there and we don't break through into the ports, because that's not a good day when you're porting and you pop through that push rod hole. That's not a good feeling. Intake and exhaust manifolds kind of depends on the performance level of the head, what we're going to do with those. A lot of times we're trying to maintain the interface to a factory manifold location on the intake side, and a little easier to raise the exhaust a little bit, but can't get too wild with it most of the time. So you've got that constraint that you've got to work around and create a series of cores that are going to be able to work and draft properly and set together and create all the proper geometry in the proper location. Spring pads, I mean, we can look at this cross section here and see this spring pad is protruding a bit into the port. And spring pad locations, I mean, if I could move them all the way out of the port, way up, I would love to do that. But of course, that's a trade-off then in valve length and weight and in rocker locations and push rods and so on. So we've got this balancing act that we have to do to not get too much protrusion, maintain enough wall thickness, and try to push it out of port so that we don't inhibit good performance through flow. And the valves themselves can move around a little bit. It's always fun. It's kind of one of the earlier portions in the design process typically is where the valves are going to be and what sizes are they going to be. And that's dependent on the bore constraints. And then of course the manifold and the port itself is going to be affected if you stand up a valve or if you cant it over. that's going to change a lot of the machining and a lot of the interface with other geometries within the head. So it can get a little bit tricky to deal with some of that stuff, but that's half the fun. So the design of castings themselves, one of the most important things that are on a casting are the tooling points. And a lot of times, you guys as an end user or a machine shop, you won't see tooling points on the head because they get machined off sometimes. But they are very important. It tells us where to start in the casting. Where is your zero datum in that casting? And typically we use 3 points on the deck, which I've highlighted in red here. We use 2 points on either the intake or exhaust manifold face, and then 1 point somewhere longitudinally along the head. And that stops all the translation and rotation. And from there, we can start popping holes in the head, get some head bolts in, get some dowel locations, or create a new datum off of those, and really know where we are in the casting. And if they're still there by the time the end consumer gets the head, if you're in a machine shop and you're trying to figure out, this head, these two heads seem a little bit different. If the tooling points are there, you can take those points and measure up to the deck or measure to a feature and try to figure out if there's some variation in the casting itself or some variation in the machine process. So it's not only good for the initial machining, but it's good for the QC process. So to get the casting onto the machine, you got to fixture it somehow. And a really common way to do that, a lot of manufacturers use, is to put what we always called ears on the casting. So you've got these ears that stick out the end. And in this picture, you can see this one has been machined on this surface. So, and then has some holes drilled in it, probably some doweling there, so that from those tooling points, we've created new datums now, and you can load this picture here as a, on a 4 or a 5 axis machine. The head's going to go through and get, a whole bunch of features, machining features created in it from those datums. So if you see a cylinder head that's machined off completely flat on the end, it's a pretty good sign, pretty common that had some ears on the end of it that were used during the manufacturing process and then were cut off in one of the last ops. Ears are also a nice way to do it because you can close over the ear and create the ear in the cope and the drag without having to have an end core in there, which adds cost and complexity to the casting. So this is a common method. It works really well. A lot of companies use it, and that's why you see those here on the bottom, these just machine flat. So I talked a little bit about wall thickness in the pushrod area. This is always one that we've got to deal with and fight. If I could have my druthers and not worry about anything, I'd just have perfect uniform wall thickness everywhere in the casting. And that casting, it would pour so nice, and you get such good metal in it and not have to worry, and life would be beautiful. But that's not the real world. We've got different cross-sectional thicknesses to achieve different goals in the machining. Typically our deck, we get a nice thick deck in aftermarket castings to help with added combustion pressure and really stiffen things up. And then we're going to have areas like the guide boss here. That is just going to be when the casting is made, there's no hollowing feature in there or anything, so that is a thick portion of metal right there. So you can see in here, it changes throughout, and it creates challenges during the casting process. But there's ways that the pattern makers and the foundries can deal with that and run some simulation. And then those risers that we talked about, we can change the location of them, the number of them, we can insulate them, and really try to control the way that the casting solidifies. And then, the casting itself, especially with if we're talking about cylinder heads with cast ports and cast chambers in them, we're going to end up with thicker than desired wall thicknesses in performance places like that push rod area, or maybe around a head bolt, so that we can have a factor of safety that if there is some shrink that didn't quite occur the way we thought it would, or there is a little bit of shift in the cores, we're not going to break through the casting and have to scrap a bunch of parts. So we add a little bit of factor of safety in the form of thicker walls. So ports, ports and chambers are the glory portion of the head, the thing that everyone looks at first when we're at trade shows or in a shop. The first thing that someone usually does is come and, stick their finger in a port and feel the short turn. So how do we make the ports? You can see here, the most common method is to group them onto a stick. So you get all 4 ports and you tie them together outside of the intake flange. And that helps with that relative core shift and relative shrink of the intake ports to themselves and the exhaust ports to themselves. And it also makes it a lot easier and faster to set the cores. So when you do that, you got to make sure, since they're not individual cores, you can't really draft them like sideways, like outward. So they tend to be drafted in what I call the vertical direction. This one's sitting flat on a table here, but that would be vertical in the mold here. And the result of that is you get this parting line that kind of runs around the port as I've drawn on here. And you'll see that in the casting in a cast port situation. You'll see the parting line in there, and you'll also see some draft in the walls, because there's, from that parting line, we got to draft the top in and the bottom in, and so you'll see a little bit of non-ideal geometry in a cast port. And one of the ways that we deal with that is to come in and do a port match, which you can see in this bottom picture here. This one has been port matched where it meets the exhaust manifold. Here we can see that parting line. So that was created when this is a big block Chevy intake port, and this was created when the core box had to separate. So when we filled that core box with sand, some of it gets into that joint, and you see the remnant of it. And then this head has been port matched, been come in, and I've got this little drawing that I did. I'm an engineer, I'm not an artist, so bear with me on this, but the original, I've exaggerated things. The original cast port would have walls like that, where we've got the draft coming in, and then we come back in the red here, and either in a single pass or in a multi-pass with a lollipop, we're going to come back and create the desired final geometry to properly mate up with our intake manifold or our exhaust manifold. And that's always a challenging thing, to get a casting to blend nicely into machine work is tricky. So if you see a head that's got a really nice smooth transition from that machine work into the casting, go and pat the engineer on the back. So cast versus CNC ports. Of course, compared to 20 years ago, we're seeing a lot more CNC ports. It's become so much more common to fully CNC a cylinder head, which is awesome. And if that head is designed from a clean sheet and that port is designed at the same time the casting is designed, we design an undersized core for the intake and the exhaust, knowing roughly what that final geometry is going to be, so that we ensure that we get full tool contact and full machine surface cleanup. I mean, I hate to see heads where a clean sheet design head where there's a little a shadow or a non-cleanup section of cast material in there. That's just that hurts. If you're the engineer and it works out that way, then you got to kind of go back and try to fix things. And in a CNC port, we can ensure that we get that full cleanup, because we can also account for the shrink with those undersized ports. We also get really consistent geometry, much more consistent than the casting itself, because shrink is not a player in it when we're on the machine. We locate on the dowels and then come in and create those CNC ports into the chamber, and repeatedly, consistently, accurately where that port is going to be every time. We can also get away with, at that point, machining thinner wall sections. So I'm going to go back again to pushrod poke, and if we're machining that port and on that same setup, we come in and we final size that pushrod geometry on the outside of the port, we can get a nice thin wall through there where I'm confident that it won't break through, but it's not going to offer as much flow resistance as I would have to have for a cast port to have the same level of confidence that it wouldn't break through. The chambers. So when we create the casting, the chamber is usually the locator for where the ports are going to end up, and they'll what we call print through into the chamber geometry. That chamber can be made either in the drag, in sand, or in another type of core we call a slab core, or sometimes we'll use a chill. And the chill is essentially a piece of steel or iron, or sometimes even aluminum, that can be placed in the mold, and as that casting is solidifying, it will much more rapidly than sand, it will draw heat out of the molten aluminum and start the solidification process in the combustion chamber or in the location wherever that chill is. I've seen them on the deck multiple places or up in the spring pockets. And it creates really good metal with good material properties in those locations. So those chills are pretty cool. You won't really be able to tell most of the time if a chill's been used on a casting because the features associated with it tend to get machined away. But then there's different the printing method, how the chamber and the port meet each other, and then how we control the movement leads to the accuracy of the final cast cylinder head. So there's some different strategies that are used, and you get different results with them, and some are better at sometimes and better at others. I don't have a definitive answer on what you always do. And then of course with a CNC chamber versus a cast chamber, we can better control some of the geometry again in there. The transition of the valve job into the chamber can be done really nicely, and the bossing for the spark plug can be made so that there's no sections where we're going to get, again, non-cleanup, or where we get too thin when the tap is run through and some of the material breaks away around the threads for the spark plug, and you end up hanging that spark plug into your chamber, and you're going to get a hot spot right there. With the well-designed CNC head, you won't see that. You'll see a nice bossing around that spark plug, and you'll get a really nice transition from that valve job up into that CNC chamber surface. Another thing that's fairly easy to do on a CNC chamber versus a cast chamber is to have some undercut, and that means like if you were to like scallop out the area around like the exhaust valve for enhanced flow in that area. If we've pushed the exhaust valve towards the bore wall a bit, and it's getting choked in that area, it's getting shrouded, we can go scallop that out with a lollipop in the porting process and get some flow numbers back up. Whereas with a cast chamber, you need to have the draft again so that the core boxes can separate. Guide bosses are always a fun one because you don't want too much material in the guide boss, and they interact with the port to really kind of set how the efficiency of that port is going to end up. They also have to support the guide, and they need to transfer heat out of the valve is bringing a lot of heat up through the stem out to the guide, into that guide boss, and then into the water jacket. So really important part of the port And it's a balancing act of getting them big enough to support the guide properly, and in a cast port, allowing for that little bit of the shrink and the core shift to happen without splitting. I'm sure many of you out there who work on cylinder heads have seen split guide bosses, and it's never good. So getting enough material in there is important to allow that machining process to happen. We'll usually, in the manufacturing process, that'll be created in the same setup that the seat bore is created in, so you get good concentricity. And we'll come in and mill a flat on it, and then drill that through, and then finish ream it. But that flat has another purpose to it, and that purpose is that when that guide gets pressed through, we've got a couple thou of press on that guide, and you're not going to push material out from a really thin interface. As the geometry of the guide, the cast geometry, comes into the machined hole, if you don't have a counterbore there, you're going to push material out. You'll see that in the port. It doesn't look good, and it tends to just come off. So not ideal. That counterbore, I always like to do that. It's a nice feature. And then if we CNC the ports, again, we can get in there, and you can really thin out that guide boss accurately, and know what your final geometry is going to be consistently, repeatably, accurately. Seats, another super important aspect. The seats are going to be determined by the machine features, and the subsequent casting and support material around it is going to be determined by the design diameter of the valves, the valve spacing, and then the seat diameter that we want. A lot of times you'll see cylinder heads with interlocked seats in them, and that just has to do with the amount of space in the chamber. Again, that we're constrained by the diameter of the bore, and then if we're trying to make a performance head with big valves in it, you just run out of space. So we interlock those seats, but it does take an extra machining op to make that happen, so the cost of production goes up a little bit. And sometimes we'll get to a point where the seats are really close, and you end up with like a sliver of aluminum in between them, and that's not ideal either, because that can burn out and lead to hot spots. So oversize the seats a little bit and force that interlock, just to get rid of that feature in there of having that sliver in between the seats. And of course, the seats themselves end up getting pressed into the head, and that creates stresses within the casting. So we've got to have enough support material in there to make sure that those are held properly. Dropping a seat that's chaos in an engine. So seat support is really, that's going to just be determined by what the operating conditions are, the performance level of the head. Bowls, short turn, everybody's favorite part of the port. The short turn is probably the most critical spot, and that transition as you come through the port and you make the turn and you go into the valve job and then out in the chamber is what makes or breaks the head. I mean, that's the spot. So that's tough. That's tough to do with a cast port, to get a really good, accurate, consistent transition from that port into the seat, into the valve job, into the chamber. And as such, we tend to have some sort of blending that goes on in there. There's a few ways to do it. One is to just go in there by hand. A lot of you, I'm sure, have die grinders and have gone and done bowl work and clean that area up, and you've seen exactly what I'm talking about, where there's mismatch in there and it just doesn't look very good. So hand blending, it's fairly cost effective, not great, but not very repeatable, and it's also time consuming. So another way to do it is with what's called an axisymmetric bowl blend, or a bowl tool that's going to just rotate around one axis, and we're going to bring that up into the port, and it's going to clean up some amount of the port, but it's got to do it in a straight line, so you don't end up being able to come around in the corner of the short turn and really make a nice blend in there. So the next option is to do a multi-pass blend and come in with a lollipop on a 4 or 5-axis machine and create some really nice geometry and come around that turn and blend things in nicely. Tricky to do, but gives you a really good result if you're not going full CNC. So water jackets, kind of the unsung hero of the cylinder head. Super important part of the head. The life of the head in most applications depends on having a good water jacket in it. It's going to remove heat out of the head from the combustion process, out of the seats, out of the guides, out of the exhaust, and send it off to your heat exchanger. But they're tough. They're tough to design, and they're tough to make out of sand because you've got to move ports through them. We've got head bolt columns that are popping through. We've got spark plugs, we've got injectors, we've got oil drains, we've got oil supplies. So all that stuff has to go through the water jacket, and it just little by little just carves away at that thing. And especially in performance heads where we want a little bit of extra meat in the ports so that someone can go in and do some porting, that comes out of the water jacket. So it gets thinner and thinner and thinner, which is then tough to produce in the sand core box, and tough to get that box to completely fill with sand sometimes. So there's different tricks and different ways to get that box to do that. And then sometimes you'll see like a piece of wire in a cylinder head you're working on in the water jacket. It's like, why? What the hell? Where did that come from? There's a piece of wire in here. Well, that would be sometimes in these really thin sections to add strength. We'll put a piece of wire in the core box, and then the sand surrounds it, and when the sand gets broken out, abandoned in place. So that's where that comes from. Of course, they have to be drafted. Also, the box has to come apart, so that draft again thins them out, makes them tough. So when we pour the casting, because of that geometry and because of the cross sections being fairly thin, they can be prone to warpage or float during the process, which changes the location and shape of that water jacket and compromises our wall thicknesses. So that factor of safety again coming into play. So some ways to mitigate that are to use chaplets, which is like a piece of aluminum that's put in and melts into the head. I don't love chaplets. Or to use core prints. And that's where on this bottom picture here, you can see some core prints that have been plugged with a freeze plug. You also see them with a pipe plug or an ORB. And the purpose of that, that's, we don't want oil and water mixing, obviously, but to make the casting accurate enough to be able to machine consistently, we poke those through so that the water jacket is locked in place and ends up where we want, and then come in and plug the holes at the end. 3D printing. So 3D printing is really cool stuff, and it's probably the future of where a lot of this is going to go. There's a couple aspects of it. One, I'm talking about sand molds here, but laser sintering, creating a cylinder head from nothing in one shot it's not quite there yet, in my opinion. So I'm not really going to talk about that. But the 3D sand stuff is really exciting, and it's getting closer and closer to being more mainstream. And essentially what that does is it's similar to a similar concept to the laser sintering type of 3D printing. And what it does is it lays down a bed of sand and then comes in and prints binder in all the places where you want a core. And then it lays down another layer and prints binder again, and so on and so forth. And you build this up, and then you come back at the end and you blow away all the loose sand, and you're left with this core. Pretty freaking cool. Also cool because you don't need draft in it. There is no core box to separate, so you don't have to worry about draft. You can have these undercut regions and stuff that would be really hard to produce in traditional pattern making becomes really easy in 3D printing. You can also tie the core package together. So rather than having a bunch of individual pieces that get set into the drag, you can have one big core package that gets set into the drag. The caveat there being that you have to have enough access to get in and blow out all that loose sand, or you'll get a bad casting. Also, you're not tied to geometry. So when you make a core box, that's your casting, and it takes a while to make those core boxes, and they're not cheap. So we try not to change them at all. And especially on something like a shell core box that's made out of iron, man, you're gonna get some bad looks from the pattern maker if you want to go change your shell core box. So 3D printing though, the 3D printer doesn't care. Send it a new file, it'll print whatever you tell it to. So you can rapidly iterate and change the geometry all the time if you want to. But currently it's a bit cost prohibitive at the moment to produce that on scale. I've had some projects where we've used it and it's turned out really awesome. And personally, I can't wait until that is a more viable option. There's more places with printers out there and the cost drops. And man, it's really going to open the door to some really cool cylinder heads. So how am I doing on? Let's see. So that's basically it. I just wanted to get you guys info about some insight into when you look at this stuff, like why did he do that? Like why is this like this? Why didn't you just make it this way? So hopefully this has helped a little bit in understanding the whole process of the casting and the design process into that finished product. And I think that's about it.
Well, Matt, that was a great presentation. I mean, you're covering a little bit of untouched territory that we typically take for granted. I think is a little bit as us working on cylinder heads, especially if you're porting and doing that kind of stuff. I mean, I'm sure there's many times that we've swore at people like you, like that they're building these things because we're just like, what were they
Absolutely.
thinking?
Yeah. No,
but
I know. Believe me, I know. Yeah.
So it's cool to see just what goes into it, and same thing, realizing just there's a lot involved, and when you start paying some bigger dollars for this stuff, now you know why. I mean, it's more than just the machining process. So
absolutely, there's a
excellent.
lot of thought that goes in it, a lot of experience. I still learn new stuff all the time about the best ways to design castings, and it's a really fun field to be in, and yeah, I love it. It's great.
Yeah, no, you can tell you're passionate about it, which
Oh yeah.
is pretty cool for sure. We do have a couple of questions that have come
Excellent.
in, and the first one, it's kind of a multi-tiered question. I'll
Okay.
work through the question and let you answer sort of one thing at a time. But what they're asking is, let's just bring it up here. What do you consider a safe wall thickness in the port around a water jacket or pushrod boss?
I mean, so from a preliminary design standpoint in the casting, I mean, usually somewhere around like 200 wall from a design criteria is pretty safe. Um, and then when you're if you're working on a cylinder head that had cast ports in it and you want to create a little bit more performance and come in and add some value to your customers by doing some port work, some calipers, some outside calipers and some inside calipers are really good to have so that you can reach around and try to check. Castings do create problems when trying to measure wall. The geometry can get pretty tough. But I've taken pushrod walls porting, down into the 80 to 100 range and maybe even a little bit further. It's always the thinner you get, if the casting isn't designed with a way to tube the pushrod, so enough bossing material, like round bossing material on the outside of the port to add a tube, I always err on the cautious side with slimming down a pushrod poke. Did that cover that one pretty well?
It did. And
Okay.
then, Matt, would those parameters be the same for aluminum versus iron?
No, so I don't do a lot of work with iron. I got lucky in that, around the time I've ported some iron heads, and I don't do that anymore because it's not real fun compared to aluminum. So yeah, you can go a little bit thinner with the iron stuff. I'd be comfortable with, maybe a 60 wall in that region on the iron stuff. But again, as you're doing that for your customers, uh, the thinner you go, the greater your risk of breaking through and then having to do a repair on the cylinder head.
Okay. And the last part of this question will be, and what about the spring pocket? What kind of parameters are you working with there?
Oh yeah, um, you can get a little bit more aggressive with the spring pocket sometimes because the spring. So imagine the spring pocket. You've got this round boss, and the majority radially, the majority of that has really good support. It's really when that port is diving through, and you've got this spot like right here that's breaking into the port area, and you've got some bossing around it. It doesn't have all the spring load on it, so it can get a little tricky. I mean, I've done stuff it's 100 wall in that area, maybe even 80 if I was really pushing it. Um, but a lot of that stuff wasn't, designed to. It was stuff for dyno testing um, or short duration testing in a vehicle where it didn't have to live through a lot of repeated fatigue loading.
Okay. All right. Um, Another gentleman's asked, how detrimental is it having a seat that protrudes into the port runner?
Um, it's pretty bad. So if the back of that seat, if you got the port coming in and the back of that seat is creating like a shelf right there, especially on the short turn, that will murder your flow. It'll just, I mean, it's not good. So if you can get in there and you can transition that into something that's smoother, where you don't have um, a a flow interruption in what we call the bad direction. So like if you're flowing this way and the flow runs into a wall in its flow direction, it's going to kill the flow. But if it's overlapped this way and it can kind of drop off that and reconnect to the port, it's not nearly as bad. Um, but the ideal situation is a nice smooth blend, as smooth a blend as you can get between them.
Okay. All right. Another question for
Yeah.
you.
Also, before you move on from that one, real quick,
Sure.
the more seat that you have hanging into the port, the less seat support you have in the cylinder head. So if it's not surrounded by aluminum all around, then the casting, that interference fit on the casting and that stress induced that's holding that seat in place, you're losing some of that. So that's a situation where you start to worry a little bit about um, the integrity of the press on that seat.
Okay. No, that makes sense. Matt, you touched a little bit on 3D printing in your
Mhm.
presentations, and so this gentleman's asked, when would 3D printing be the best option?
3D printing is really the best option for really low volume stuff right now. If you want to make like 2 parts, um, you know, let's say in traditional tooling, you'd be $60,000 or $80,000 in tooling plus the casting cost to make that part. Whereas a 3D printed sand mold might be, just throw this out there, $5,000 each, $4,000, $5,000 each, something like that. So if you're doing really unique geometry, low volume stuff right now, then 3D printing sand molds are a really good option. Also, if you're trying to do some crazy geometry that has a bunch of uh, strange internal passages that would be difficult to make in a traditional pattern making method, again, 3D printing becomes a really good option.
Okay.
And I like
All
3D
right.
printing a lot. I can't wait till, like I said, till that cost comes down. Like that's going to be used all over the place, and it's going to create some really cool stuff. So if you're thinking about dabbling in 3D printing, getting a little experience under your belt now is not a bad idea if it's cost effective for your business, and to be ready for when it's a lot more widespread.
Okay. All right. Couple more questions here for you, Matt. Again, we're just going to respect everybody's time so they can all get back to work and go make some money. And same with
Yeah.
yourself. I'm sure you're you probably got stuff you could be doing.
Yeah, it's time for lunch.
It's getting that way. I hear
Yeah.
you. I'm on Pacific
Yeah.
time as well, so we're getting there for sure. Is there a parameter that you work with in regards to core shift? You mentioned that, and like what is allowed before maybe you have to do a change to the mold?
Yeah, that's a good question. Because you see core shifts. I mean, you can see core shift on a new tool, and then the more you use a tool, the more castings you create out of one tool, it wears out. I mean, you're blowing sand at a fairly high velocity into these boxes, and it just wears them out over time. So you start to get looser and looser tolerances. Um, if you're seeing like let's use the throat area of a port, and like where, I mean, since we had a question about a hanging seat, like if you're seeing a seat hang by, you can measure it by like 30 thou, like, oh man, I'd be hard pressed I wouldn't be very happy with that, if it was shifting around that much. Maybe 10 thou, 15 thou is acceptable. But again, it's sand. I mean, it's tough. It's not an easy process. And when you set that sand in, we tend to have some glue in there that helps hold it in place. And um, a lot of it also depends on the experience of the person assembling the mold. I mean, it's a lot of this stuff is still done by hand. So someone's literally taking that core and like setting it into the mold and like pushing it down or pushing it down and right, or like however it's made. And that can really affect it. So yeah, if you're seeing core shift that's 30 thou or so, I'd start looking at things.
Okay. All right. One last question here for you, Matt, and this is just a little bit off topic, just a little bit, but I know it's a big concern with our industry right now.
Okay.
So the question is, I mean, all our shops are having difficulty finding qualified machinists, to do the work.
Oh
So
yeah.
they're asking, where does Banks draw from? Where's Banks Power getting their folks from, or where are you? Are you going to the schools? Do you do a lot of in-house stuff, or what do you guys do
Yeah,
there?
I mean, I'm actually going to a little school event on Saturday, trying to get talent. It's really tough, and it's tough here. We're in the greater Los Angeles area, and there are a lot of machine shops and a lot of businesses doing machine work, including aerospace and especially some startups like SpaceX tend to pay really well. And SpaceX, some startups like that will even offer some equity options. So competing with that is difficult. So I've got some relationships with different colleges in the area, and I've gotten to know the instructors there, and if they've got, if we're in a phase where we're hiring and they've got some really talented students, that's a great place to go. More and more community colleges are bumping up the trade programs and starting to put out some really talented people. I was in school, in high school and in college at a time where the cultural shift had been away from shop classes in high school uh, and in colleges, and trying to go into more white collar work and sitting behind a desk, which there's nothing wrong with that. I do that. But it really put a dent in the talent base of people who are good at working with their hands and creating things. So I also find LinkedIn. I'm on LinkedIn and uh, try to post on there and read other people's posts and make connections, and that tends to be a good spot to find people as well. And then industry connections like AERA. Just talk to people, get to know as many as you can, and um, you, you know, maybe you're looking, maybe you're not looking, but people will pop up, and if they're good, grab them.
Yeah, no, that's a good point, Matt. Um, usually the good ones are working already. They're working,
Yeah,
so
yeah,
you almost got to steal them. But no,
yeah, a little bit.
that's a good
Yeah,
answer.
yeah,
Well, any questions that we've got left over, Matt has agreed. I will forward them to Matt, and Matt will get back to you for sure. Matt, I thank you again for putting this together for us. Like I say, you really gave us an inside look at something that we just don't get to see every day. So it much appreciated. You did a great job, and
absolutely.
nice to
Thank
see
you.
that. Yeah, nice to see the background and what's going on there. That was
Yeah,
yeah. So thanks again, and like I say, I'll forward you any questions that come through. So
fantastic. Thank you very much.
yeah. Right now, what we'll do is we'll go back to Amanda, and we're just going to wind things down, and we'll let everybody get on with their day.
First off, you will receive a little pop-up when you exit today, and this is just a survey. Take a moment, let us know how we're doing. If you have any additional questions for us or for Matt, you can toss them in there. And as Rob mentioned, we will get those answered for you. Also, if you want to reach out to AERA at all, you'll see our phone number is listed there, 815-526-7600. Or you can always email Rob or myself. Our email addresses are listed as well. And we're happy to help with any questions you may have, either about the webinar today or anything else. So once again, thank you everybody for taking time out of your day. We greatly appreciate it, and we hope you have a great afternoon.